Okay, welcome back everyone. Let's get started. So today we're going to review the basic linear algebra that we need for this course. And just to sort of start off, we might ask why do we want linear algebra? Why do we need to use it? And basically one motivation is that it gives us a way to represent and analyze systems of linear equations. So if I have this system of linear equations, you can see two equations and two unknowns. We can rewrite this if we want as a matrix with the coefficients 5, 2, minus 4, 1 times a vector x1, x2 equals a vector 3, 4. And we can basically give these things names, like we can name this A, can name this X. I'll explain these underlines in just a moment. Can name this B. And, sorry, I guess down here I have space to write these things in. I'll put them down here. Okay. And so once we have it written this way, you can see that this is just a lot more concise than this. And once we have it in this form, we can apply basic ideas from algebra to it, like the idea of an inverse. If we want to multiply both sides of this equation by the same quantity, A inverse. In this case, A inverse is the inverse of this matrix A. Together, they essentially cancel and give an identity matrix. We'll talk about inverses in a few more slides, but basically this matrix doesn't always exist, but for this problem it does exist. And once we cancel A and its inverse, we have now a direct expression for X, which is something we can evaluate. And again, more details soon, but this is just one of the reasons why linear algebra is useful. It gives us a concise way of understanding and writing things, and once we see it in a simpler description, we can see what we can do with it. Okay, so let's just start out by talking about the notation that I'm going to use in this course. So when we have non-bolded quantities, those are going to denote scalars. So like if you have a little c or a big C, neither of those are bold, those are just scalar values. Now, if you see a bold-face quantity, like this is a bold X, then that is going to, and it's lowercase, that's going to represent a column vector. Column vector is this column-wise stack of scalars. In this case, this is a vector in R3. Now, if you see a bold uppercase letter, that's going to denote a matrix. So here we have capital A bolded. That gives us a matrix. A matrix can have more than one row, more than one column. And the reason that I'm using these notations is that so you can easily, when you see an equation, you can immediately understand its structure. You don't have to search for some definition. How did he define, what is this A? What is this X? Like, you know that it's a matrix, you know that it's a vector. And in particular, this is a column vector. So if we want to write a row vector, like x1, x2, x3, I couldn't write that. Can anyone tell me why, according to my rules, this is, how do I fix this expression? I need to put a transpose on this. Okay. Because basically, we're saying whenever you see boldface X, or when I'm writing things by hand, I'll use an underline. Whenever you see this, you know that it's a column. So that means whenever you see a transpose column, you know that it's a row. Okay. This is super useful to just understand what's going on. Any questions so far on this notation? Okay, this is super important. So when you're writing your exam solutions out, this is pretty important to put underlines places, because if you write an expression where I can't understand whether you meant a vector quantity or a scalar quantity, I can't give you full credit for that, because you didn't express yourself precisely. Okay, so I'm trying to express myself precisely here. Okay, so now let's say we have a matrix, and I want to extract one of the elements from inside that matrix. So in this course, I'm going to use this square bracket around the matrix with sub ij to extract the ith row and jth column of that matrix. So sometimes when you take this matrix A and you extract the ith row and the jth column, you get this lowercase aij. But this is not always true, because if I take that same matrix and I transpose it, what happens is I end up flipping the rows and columns, and this will no longer hold. The I and j will get flipped. Okay, so you just always have to be clear with exactly what you mean. If this is what you mean, then you should state it. Okay, so the transpose is just a way to swap rows and columns. So we talked about up here, if I have column vector x defined this way, and I transpose it, it just flips this quantity around. If I have this matrix A from above, and I transpose it, then I'm going to get the first row ends up turning into the first column, and the second row turns into the second column. Okay, so basic properties of the transpose is that if you apply the transpose twice, it cancels out. So A transpose, quantity transpose is just A. And if you apply the transpose to product of matrices or vectors, you apply the transpose individually, but you also have to reverse the order of the product. So this is B transpose, A transpose. Okay, so these are just basic properties. I'm assuming you guys know all this, so I'm just kind of going through to jog your memory and emphasize, what are some of these really important key things. Okay, any questions on notation? Great, so moving on to matrices and vectors. So there's many ways to decompose a matrix into some vector structure. So one way is we could express this matrix A here, which is specified like this. We could express it using these three columns. So here A1 is the first column, which has to be A11, A21, and the second column would be A12, A22, and the third column would be A13, A23. Okay, but that's not the only way we could do it. Sometimes we like to talk about the rows of a matrix. So for that same matrix, we could instead define two rows, A1 transpose and A2 transpose, and then say that the A matrix is a vertically stacked concatenation of those two row vectors. Okay, any questions on this? Okay, so another important thing is sometimes you'll see a quantity like this. It's bold A sub I. So if you remember, bold A means a column vector, right? So this bold A sub I does not mean the ith element of that column vector. This bold AI is itself a vector, and it's the ith element in some sequence of vectors. So for example, over here. We have a sequence of vectors A1, A2, A3. If I want to talk about the ith one in the sequence, I would get AI. It could be any of those three. If I want to talk about the ith element of a matrix, of a vector, what I could do is I could say, okay, I have a vector A. Now I'm going to extract the ith element, and I might call that AI, where this is a scalar. And this is a vector. Okay, is that making sense? Okay. Any questions so far? Okay. So the thing we'll see most often with linear algebra is multiplication of matrices or possibly vectors. A vector, you can basically say, would be like a matrix with one row or one column. So it's just a special type of matrix. So if we have two matrices, A and B, and let's look at their dimensions carefully. If we're saying A is an M by P matrix and B is a P by N matrix, because they share this inner dimension, P, we can multiply them together. That allows us to do this multiplication. If they do not share that inner, that same dimension, we cannot multiply them. It just doesn't work. So if we're looking for the main equation behind matrix multiplication, we could say it this way. So this would be the ith row and kth column of A. This is the kth row and jth column of B. Here you can see that the inner dimension is the same, and we are summing over that inner dimension. To see this perhaps more concretely, we could look at this example down here. So actually, let's try to visualize this. I find this visualization of matrix multiplication to be super useful. So let's picture A as some matrix like that, and let's picture B as a matrix to the right of it. And let's furthermore denote the integer dummy variables that we're going to use for multiplication. So K is used to index over the columns, right? That's how we're using it here. It's indexing over the columns of A. We're also using K to index over the rows of B. Now you'll see that we're also using I to index over the rows of A, and J indexes over the columns of B. And when we do this matrix multiplication, essentially what we're doing is we're saying this is a new matrix C, and C is going to have those outer dimensions. Let's say I goes across its rows, J goes across its columns. And what we're doing is we're taking, to get this element here of C, the top left element of C, we're taking top left of A times the top left of B plus the next along that row of A times this one times the next one of A times this one times the next one times this one. So we're basically doing those multiplications, and then we're summing all of them up, and that gets stored here. Okay, so this is very fundamental. Hopefully You guys remember this. This is something you have to really internalize because it's at the heart of everything we do. So let's take a look at that again for this example down here. So we have, to get the top left element of the product, we're going to have A times E plus B times R. So A, E plus BR. To get the next element to the right of that, we're going to have A times F plus B times S. AF plus BS. And to get the last one, we're going to have A times G plus B times T. Now, to get the bottom row, we use the bottom row of the first matrix, C times E plus D times R. The next one is going to be C times F plus D times S. And the final one is C times G plus D times T. And you can see when we do this, we get a new matrix that shares the same number of rows as the first one, which is 2, and the same number of columns of the second matrix, which is 3. Okay, so this is super important. And what's cool about the way all this here works is that even if these matrices are not scalars, but if they're vectors or matrices themselves, these little entries, you can still use exactly the same approach to multiply them. And we'll see that on probably the next slide. Yeah, the next slide. Okay, any questions on matrix multiplication? Okay. Is this stuff like super easy? Everyone already knows this, or is it useful to see it again?
I think it's useful to just go over one time and remember everything.
Okay, all right. So hopefully you're not completely bored. Okay, now important point. Matrix multiplication does not commute, meaning A times B is not equal to B times A. It works for scalars. Scalar multiplication commutes, but matrix multiplication doesn't commute. So we'll see some examples on the next page. Okay, so something that happens a lot is where you have a row vector times a column vector. And so here this would take the form A transpose B, where A and B are both column vectors. So when you do this, we get A1 times B1 plus A2 times B2, dot, 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 all the way to AN times BN. Now, instead of writing this kind of cumbersome long dot, dot, dot expression, we like to use summations. So we're going to define an index. We can really choose any index variable we want as long as it doesn't clash with another existing variable like n. So maybe I'll just choose the variable I. I'll use I to index across those. So now I'd have a sum over I equals start at 1, go all the way to n, and then I'm going to have scalar AI times scalar BI. And this is called an inner product. Okay, so something special, we have a special name when the inner product of two vectors is 0. That means those vectors are orthogonal. And if you have, let's say, two-dimensional vectors so that we can visualize them, they're sitting in some plane, and if they're orthogonal, that means that they are at right angles to each other. Okay, everybody good with inner product? Okay, outer product is where you have a column vector times a row vector. So column B times row A transpose. Now in this case, yes, you can do this multiplication because they have a matching inner dimension of 1, But the outer dimension now we're going to get is an n by n matrix, an entire big matrix like this. N by n. And here you can see clearly I can't just swap A transpose and B and get the same thing. In one case I get a scalar. In the other case I get a whole matrix. Okay, good. Everybody good with this? Any questions? Okay. Don't be shy about asking questions, because usually if one person has a question, many other people have the same question. So it can help when someone is brave enough to ask. Okay. Now we'll see a lot of different examples of matrix, vector, matrix multiplication. Sometimes it's convenient to think of a matrix in terms of its columns, like we can say the columns of matrix A are A1, A2, and A3. And in this case, sometimes it's convenient to think of a matrix in terms of its rows. So for B, its rows are B1 transpose, B2 transpose, and B3 transpose. Now, if you want to do this multiplication here and to express the answer in terms of these different vector quantities, you can use exactly the same logic as we applied here with scalars, but we can now actually do this with vectors. So it ends up that this is A1 times B1 transpose plus A2 times B2 transpose plus A3 times B3 transpose. And we like to write this often using a sum, so I could again, I'll just change it now. Let's say I want to use J. I'll say J goes from 1 to 3, AJ, BJ transpose. So is this thing that I'm getting going to be a scalar, a row vector, a column vector, or a matrix? What do you think? Matrix, that's right, because here it helps maybe to draw a little picture. So AJ is a column vector. BJ transpose is a row vector. So when I multiply column times row, that's an outer product. I get an entire matrix. So what I have here is just a sum of 3 matrices, which again is going to be a matrix. Okay, is that making sense? All right. So now maybe I encounter a situation where it was convenient for me to have described the rows of A this way, using row vectors A1 transpose, A2 transpose, A3 transpose, and the columns of B this way. So one example where we'll see this later is often when we have a data set, we organize it this way, where each of those rows is one element in the data set. So in this case, it would be a vector of what we call features. And then over here, we could have 3 different linear predictors. So we'll definitely see this. Okay, so if I want to do this multiplication, once again, I can use the same logic as I used over here, even though what we have inside here are row vector and column vectors. And so when we do this, we're going to get a matrix where the top left column, or top left entry, is A1 transpose B1. And then moving right, we have A1 transpose B2, A1 transpose B3. Moving to the next row, A2 transpose B1, A2 transpose B2, A2 transpose B3, and then finally A3 transpose B1, A3 transpose B2, A3 transpose B3. Okay. Now, if I ask you, what is the dimensionality of this quantity? Is this a matrix, a row vector, a column vector, a scalar? What is this? Scalar, exactly. So this particular quantity here would be a row times a column, which gives a scalar. And so we have these scalar entries in this 3 by 3 matrix. So altogether, we're going to have a 3 by 3 matrix. Maybe up here I should emphasize this is a scalar. So this is in the field of real numbers. Is everybody good with that example? Okay. Now another situation that might arise is we just like to think of A as a matrix. We don't like to break it apart. But B, we might like to break apart into its column vectors, B1, B2, B3. So if I want to do this multiplication, then what I'm going to get is I'm going to get a matrix whose first column is AB1, second column is AB2, third column is AB3. Okay, so here I have a matrix with 3 columns, and each of those columns, well, we don't actually know how tall this matrix is. We don't really have enough information. And finally, we might have something similar, but maybe A is described in terms of its rows, and then B is just kept together as one unit. And so now if we want to do this multiply, we're going to get top row of A1 transpose matrix B, and then the next row is A2 transpose B, and the bottom row is A3 transpose matrix B. Okay, so this is just for visualization. Okay. Everybody good with all of this? Any questions? Okay, great. All right, so now let's talk about some special matrices that show up a lot. So first we have diagonal matrices. What we mean by a diagonal matrix is that you can have non-zero values on the diagonal of the matrix, but 0 values everywhere else. So an example could be like this, where I have a 3 by 3 matrix with D1, D2, D3, like this. So along the diagonal, possibly non-zero, but off the diagonal, we know it's 0. And here, this is one way that we could specify this. We could say, if I look at the ith row and jth column of D, then whenever the column and row agree, which are those 3 places, I see the scalar value di, so d1, d2, d3. But if I and j do not agree, that's where this else is, then I have 0. So this is a case statement here that is often a convenient way to describe expressions where you have sort of different cases of the expression. And so in this class, I'm going to use this capital D diag. If you take the diag of that scalar sequence, it basically puts that on the diagonal of a matrix. Now, a very special diagonal matrix is the one where you have 1s on the diagonal, and that's called the identity matrix. And the special property of the identity matrix is that if you do matrix multiplication with I, whether I is on the right or on the left of the multiplication expression, it basically has no effect. So A times I is A, and I times B is B for all matrices A and B. Okay, now this identity matrix, so related idea, symmetric matrices. These diagonal matrices are symmetric, but symmetric matrices are a little bit more general. They're matrices that when you transpose the matrix, nothing changes. So A equals A transpose. So as an example, you might have the matrix 1, 2, 2, 0. So if I swap the rows and the columns, essentially the 2's shift places, but in the end you get exactly the same matrix. So invariant to transposition. And finally, another special class of matrices that we'll encounter a lot are called orthogonal matrices. These ones have orthonormal rows and columns. So that means that orthonormal is a combination of orthogonal and normalized. So it goes like this. If I take, let's say if ui is the ith column and uj is the jth column, when I do this inner product, ui transpose uj, if I and j are the same, then I get a 1. That's the normalization. These are normalized so that the inner product with itself is 1. But if I and j are different, you get 0. So that means that all the different columns are orthogonal to each other. It also works with rows. If ui transpose is the ith row of u and uj is the transpose of the jth row, then you get the same property. So if you want to express this idea using matrices, you could express it this way or this way, depending on how you want to define the u's. And so we can see that by drawing a little picture maybe of this u transpose and u. So imagine these denote the columns of u, and these, since I'm just transposing that u matrix on the left side, I get exactly the same quantities, but now they're transposed. And so now if I do this times this, since I'm doing an inner product of the first and the first, I get a 1. So I get a 1 there. If I do the inner product of the second and the second, again, I get a 1. So I'm going to get a 1 in the next position. Third and the third gives me again a 1. But now if I look at any combination of like the first inner product, the second, because they're orthogonal, I get zeros there. So all of those guys are zeros, and now you can see that I have recovered the identity matrix. So this is another way, a more compact way to express this idea. Any questions on what I said over here? Any clarification needed? Good, okay. And now if you look at this expression, you'll notice that this u transpose is acting like an inverse. It's inverting u, giving an I. Similarly, this u transpose again is acting like an inverse. So in other words, when you have an orthogonal matrix, to invert it, it's very easy. You just transpose it, you get the inverse. Okay, so those are some special matrices that we encounter. All right, moving on. There's no questions. What about operations on vectors and matrices? So one of the important ones is when we take the norm of a vector. This is a way to measure the length of the vector. But there's actually different ways to measure the length of vectors. So the most common way is the Euclidean norm, also known as the L2 norm. So if we want to be sure that someone understands we are talking about the Euclidean norm, we put a little 2 in the subscript there. And this norm is defined as the square root of the sum of the squares of the elements of the vector. And if I draw a little picture, again, here we have a plane, and let's say that the origin is here, and if I have a vector that ends up over there, x, and I want to measure the length of the vector in terms of like how the crow would fly from this point to this point. It just goes directly there. It doesn't take any curves. That's Euclidean norm. But there's other ways to write norms. There's the L1 norm. If we want to emphasize that, we put a little 1 in the subscript. And this one is defined as the sum of the absolute value of the elements. And this is also a very useful norm. For example, let's say you're a taxi driver in New York City, and you want to know how far you have to drive to pick up someone. Well, because you have these city blocks and you can't go through the block, you have to go down a street, down, let's say, an east-west street, and then down a north-south street. You have to measure distance this way. So that's also a valid unit of distance, but it's just different than Euclidean. So to go from here to here, you would measure how far to travel in that direction and then add it to how far you travel in that direction. So that's the L1 norm. And we'll see uses for both of them in machine learning. And there's many other norms too. You can put a p here and a square root here and a p power, and that's the p norm. So there's different norms, but these are the most common ones here. Yes? No, Euclidean norm applies to, we're going to stick with finite dimensional quantities in this course, but any finite dimensional quantity. So here you can see this is the equation if x is an n-dimensional vector. Yeah. But often when I draw a picture, it's going to be 2 or 3 dimensions, because as humans we can't really visualize things well beyond 3 dimensions. But the nice thing about finite linear algebra in finite spaces is that all the intuitions for 2 and 3 dimensions carry over directly to arbitrary dimensions. So if you can visualize how something behaves in 2 and 3 dimensions, that's exactly how it's going to behave in n dimensions. Nothing like really special happens differently with linear algebra. Okay. Now, if you see a norm without any subscript, assume the Euclidean norm. That's called the standard norm for this space. And if we're dealing with finite dimensional vectors x, then the standard norm is the Euclidean norm. An interesting thing about these orthogonal matrices is that if you think about that matrix as something, when you multiply by a vector, it's kind of like you're processing that vector with that matrix. It turns out that the processing you're doing is just rotation. Orthogonal matrix is like a rotation matrix. And by rotation, we mean it rotates but doesn't change the length. So it just rotates that vector around. So if it doesn't change the length, then the 2 norm remains the same. What about the 1 norm? If I rotate, would the 1 norm stay the same? No, it's not going to, 1 norm is not going to stay the same. But the 2 norm definitely stays the same. Okay, so that's the norm. Sometimes we'll talk about the norms of matrices, but not too often, and when we do, I can talk about that when we get to it. So now, the trace is a very useful operation for a lot of proofs. I'll explain why in a moment, but basically what the trace is, if you have a square matrix and you take the trace, that's nothing more than saying I'm going to sum the diagonal elements of that matrix. And the trace is a linear operation. By linear operation, we mean that if you have 2 matrices A and B and 2 scalars, alpha and beta, and they can be any matrices and any scalars for which you can add them, they have the same dimensions, that when you take the trace, you could have equivalently done alpha times the trace of A plus beta times the trace of B. Okay. So linearity is a property that we'll see often in this course, and this is just an example of linearity. Now, something that's super cool about the trace is that it allows us to commute matrices. So the trace of A times B ends up being equal to the trace of B times A. Okay, even though, in general, AB is not equal to BA. Okay, so this is super useful in a lot of proofs where we want to move things around, but we can't usually, we want to commute matrices, but we can't usually do that, but when they're inside a trace, then you can. Okay. All right, any questions on trace? Great. About the matrix inverse. So we briefly talked about this. If you have a square matrix A, it needs to be square. The inverse is the unique matrix, such that if you multiply either on the left or on the right, you get identity. Okay, now, this inverse matrix may not exist. In some cases, let's say if A is the zero matrix, I can't multiply 0 by something to get identity. Remember that we're working with finite quantities, no infinities allowed here. So we can't, you might say, well, can I multiply 0 by infinity to get something finite? Well, sometimes you can, but we're not working with infinities here. We're just finite times finite, and sometimes you can't. 0 times any finite number is 0. Okay, but when A inverse does exist, we say that A is invertible. Sometimes we say that it's non-singular. Okay, so a few important properties. If I have two matrices A and B whose inverses exist, okay, first of all, if I apply the inverse twice, A inverse and then I inverse that, I recover the original A. If I have a product of matrices A and B and I invert the product, similar to how we saw with the transpose, you invert the individual entities, but you also swap their order. Now, be a little careful. So if A and B are not square, for example, or if those matrix inverses don't exist, then obviously this is not true. So here we're just assuming that those things exist, and then this is true. And finally, one more. If you transpose the inverse, that's the same thing as inverting the transpose. Now, inverses are easy to compute when we have 2 by 2 matrices. So in this case, let's just say that the ith row and jth column of matrix A is this Aij. In that case, you have, what you do is you swap. So let's visualize. So that means the A matrix looks like this: A11, A21, A12, A22. So what I have over here is I have swapped those two, and I have negated those two. So I do this swap negation, and then I'm dividing by this quantity over here, and this will give me the inverse. If I have a 3 by 3 matrix, it's not so easy. It gets quite cumbersome. And so for larger matrices, when we compute these inverses, we tend to do this numerically. We don't do it by hand. But with 2 by 2 matrices, you could do it by hand if you needed to. Okay, any questions on inverses? Okay. What about determinants? So the determinant is a particular operation which has a nice geometric interpretation. The determinant of A is the volume of the set of all linear combinations of its columns with combining coefficients between 0 and 1. So let me give you a visual example. So here, let's just say that I have these two vectors, A1 and A2. These are two-dimensional vectors. So A1 is the vector 1, 3. So this is the first dimension of A. This is the second dimension of A. And so here we have the vector A1, like this, the vector A2. Okay, so let's consider all linear combinations of those columns that are scaled somewhere between 0 and 1. So I can scale this down to be like that long or anywhere in between, but I'm not allowed to scale it beyond here. Same with this. I can scale it to anything between 0 and there. And then I'm going to add those two things. So if I take all linear combinations of the scaled A1 and scaled A2, I will get this gray region. Does that make sense? Okay. So the volume of this region is the determinant of that matrix. Okay. So this is how we would express it with mathematical notation. Let's say that the set S is the set, that's what the curly braces mean, the set of all vectors V. This means such that all vectors V, such that V is a scaling of AI plus a scaling, B1 times A1 plus B2 times A2 plus, beta 3 times A3 and so on, where the betas can be any numbers between 0 and 1. So this recovers all the different V's in here. It's the set of all those V's, and now it's the volume of that set. Okay, so that's how we can think about the determinant. If you have a 2 by 2 matrix, the determinant is easy to compute. It has this equation here. And does this look familiar? Where did we see this?
The inverse.
We saw this in the inverse. It was exactly here. Okay. But for a 3 by 3 matrix or larger, it's a bit more complicated, and so we tend to compute determinant numerically for larger matrices. But sometimes we have to do some simple computations like this. So here I have a matrix A and a scalar C. And C is multiplying A inside the determinant. Well, what happens when I pull that C out? We end up taking C to the nth power. So the reason why, maybe I can give you an example. If I have, let's say, a matrix 2, 2, 2 diagonal matrix, turns out when you have a diagonal matrix, the determinant is just the product of the diagonal terms. So you can see the product of those diagonal terms is going to be 8, 2 times 2 times 2. Now, if I wanted to pull out a factor 2 of here, I would get an identity matrix. But when that 2 comes out, I have to raise it to the third power because I have a 3 by 3 matrix. And that expresses where we got that C to the power n. Okay. So this is very useful to remember. This definitely shows up a lot. Okay, so that's the determinants. Let's see how we're getting pretty close. Any questions on the determinant? Okay. Eigenvalues and eigenvectors. Okay, so this is how I like to think about eigenvalues and eigenvectors. When we have matrices, we can think about them different ways. We can think of a matrix as just sort of like a table of numbers, or we can actually think of a matrix as like a black box that acts on a vector. What I mean by that is if I have a vector V going into this matrix multiplication box by A, what's going to come out is going to be A times V. So here we're thinking of A as like a system, V is like a signal, V goes into this box, and out comes A times V. So it's kind of an unusual thing. If I take a particular vector, maybe like a square wave, or it has some particular shape, and I put it through this system, it'd be kind of an interesting and maybe strange occurrence if what comes out is exactly V, but just a scaled version of it. That's a special thing that doesn't usually happen. Usually when I multiply a vector by a matrix, it gets completely changed. But sometimes all it does is get scaled. And when that happens, you have a special situation. That particular vector or signal is called an eigenvector, and the amount that it gets scaled by is the eigenvalue. So in other words, if I stick in an eigenvector of A into this black box thing here, out will come lambda V, where lambda is a scalar, and it's in particular the eigenvalue that corresponds to the eigenvector. Okay, so that basically that's the idea behind eigenvalues and eigenvectors. It's this special vector that when you multiply the matrix on the right by that vector, you just get a scaling of it. Okay, so this, if I have a square matrix of, let's say, dimension n by n, I can get this to happen with possibly n, up to n different vectors v. And if I stack those n vectors, little v, into this matrix, capital V, then I can express this whole thing. This is for I going from 1 all the way to n. I can express that like this. So what I've done is I've just stacked the different v's, the different little v's here. And now, because I have a diagonal matrix, this is a diagonal matrix. Let me visualize this for you. So we have V is going to be that. Lambda is going to be a diagonal matrix. And when you do this multiplication, you are going to get a matrix where the first column is going to be, how do we think about this? Let's maybe move step by step down that column. So the first element, it's going to be this times this. But because of the zeros here, this multiplies this, and I basically copy the first entry of that over here. Then I move down to the next row, and the same thing happens. I end up copying the next element down here and so on. So finally what I get is I get in this first column, I get this scaled by whatever number this is. For the second column, I get the next one scaled by whatever number this is. So that's kind of illustrating what's happening here. Okay, so this is eigenvalue, eigenvector pairs. Everybody okay with the general definition? Okay, so now, in the general case, the eigenvalues are complex numbers. If you want to get a sum of the eigenvalues, you can just take the trace of the matrix. If you want to get a product of the eigenvalues, that's the same thing as the determinants. Something special happens when the matrix is symmetric. In that case, the eigenvector matrix is orthogonal, and the eigenvalues are all real valued. And so one of the implications of this is that the matrix is invertible if and only if there are no zero-valued eigenvalues. And also, because of this orthogonality property, we know that the transpose equals the inverse. We can basically multiply things on the right by V inverse, and we have this special eigenvalue decomposition for symmetric matrices. This definitely shows up a lot, for example, when we talk about PCA. And we have a few names. A symmetric matrix A with positive eigenvalues is called a positive definite matrix. And one of the properties of positive definite matrices are that when you put them in a quadratic form, meaning you surround it by vector x transpose on the left and x on the right, You do this multiplication, you get a scalar. That scalar is guaranteed to be positive. And similarly, if you have a symmetric matrix with non-negative lambdas, we call that positive semi-definite, and it gives you this quadratic form that is non-negative. And we'll see examples of this show up. And I have a couple slides left, but I think this is a good time to stop. Next time, we'll finish up this, and we'll just get a little experience playing with some matrix vector multiplication stuff that is going to be very useful when we move on to the next unit. I'll see you guys on Friday.